Then let us see the next topic, which is electrophiles and nucleophiles. See, electrophiles are positively charged electron deficient species. Now, and remember, nucleophiles are, symbol is Nu minus. These are electron rich species. They have lone pairs, so that makes them electron rich. Now, these electrophiles and nucleophiles can be neutral, like let me give you example of BF3, AlCl3, FeCl3. All these are your neutral electrophiles, or B2H6, and they can be your cationic species, like we can have CH3 plus, we can have H plus. Like all these are what ionic species, which are electrophiles. Whereas in a very similar way, we can have nucleophiles, like water is a nucleophile, ammonia is a nucleophile, amines are nucleophiles, ethers are nucleophiles because they have lone pairs. Whereas we can also have what CH3 minus, OH minus, NH2 minus. All these also are your ionic species, anionic, which are actually electron rich, so they can acting as a nucleophile. So we can have neutral or ionic both categories of electrophiles and nucleophiles. We need to remember that they always attack those areas which are electron rich, and they always attack those areas which are electron deficient. That is why we call them nucleophiles, we call them electrophiles. Now they plays a very important role, and specifically in addition reaction and substitution reactions, and that is how we name such type of reactions. Now let us see the electron movement in organic reactions. See, electron movement always takes place, and it mainly takes place in those examples or in those compounds where we have what phenomena of hyperconjugation, or what we have the phenomena like resonance or tautomerism. But what we need to know is that we represent these movements with the help of arrows. Now the movements mainly takes place in three different ways, like which has been explained here. The movement can be from a pi bond to the very next adjacent covalent bond. So this pi bond gets shifted to the next adjacent normal covalent sigma bond. So what happens is this atom through which it was bonded acquires a positive charge, and this pi electrons get shifted to the next one. Another thing is that second type of movement can be from of a pi bond to the atom through which or to which it was bonded. So this movement of the pi electrons to the atoms to which it was bonded is another type of movement, in which what happens is the atom acquires a negative charge, and the atom from which the shifting has taken place acquires a positive charge. Another type of movement can be of a lone pair to a normal, to the very next similar covalent bond, and due to which what happens is the shifting of the pi electrons can also take place within the molecular species. Like here, the bromines one lone pair is getting shifted towards the sigma bond, and as a result, this carbon's pi bond gets shifted to the CH2 group, CH2 carbon. So this bromine acquires a positive charge, and this CH2 acquires a negative charge. These are the three main types of movements which takes place, which are represented by these arrows. Now let us see the electron displacement effects. See, the displacement of the electrons in the carbon chain or in the organic compounds takes place mainly because of the certain groups which are there in these compounds, which actually influences this movement of the electrons, the bonded electrons. And as a result, what happens is the polarities are introduced, and as a result, the reactivity of the compounds gets affected. The first of its type of the electron displacement to be studied actually is called inductive effect. We also call it I effect. I means inductive effect. Now what is this effect is? It is the introduction of partial positive or partial negative charge all along the carbon chain due to the presence of certain specific groups, which itself requires either a partial positive charge or partial negative charge, is called inductive effect. Let me explain it to you with this example. Like suppose we were having this N-butyl, and we were having what phenolic group attached to this. Now this oxygen, we know that is more electronegative than carbon, so the shared pair of electrons will be more towards oxygen. So this carbon number 1 of this 4 carbon chain acquires a partial positive charge, and oxygen acquires partial negative charge. Now as a result, this carbon number 1 becomes electron deficient, and the shared pair of electron which it is sharing with the carbon number 2 also gets attracted more towards carbon number 1, and as a result, carbon number 2 also acquires what partial positive charge. But of course, this partial positive charge will be less than what the carbon number 1 is having. having, and subsequently all other atoms of the carbon atoms of the chain also acquires partial positive charges, but their magnitude keep on decreasing, and that is why we neglect this positive charge after carbon number 2, because that becomes almost insignificant. So this introduction of partial positive charge by a certain groups which itself acquires a negative charge is called minus I effect. Is called minus I effect. And we can easily make out from here is that all those groups whose atoms through which they are bonded to the carbon chain are more electronegative than carbon will be introducing what negative or minus I effect. Now thus such groups can be your nitro group, your cyano groups, your acid group, your halogens, your nitroso group, so all these alcoholic group, amine group, so all these sort of groups, ether group, so all these groups introduces what minus I effect to the carbon chain. Now this inductive effect can be exactly of opposite type also. Now, let me give you an example of this. Like if we are having, suppose, like a group of this, the example of the Grignard reagent, which is N-butyl magnesium bromide. Now in this case, this carbon number 1 of the chain is basically what is more electronegative than magnesium, so it itself requires a partial negative charge. Magnesium is having a partial positive charge. Now as a result, the electron density at carbon number 1 is very high, and due to which the pair which it is sharing with the carbon number 2 gets repelled towards carbon number 2. As a result, carbon number 2 also acquires a partial negative charge, and subsequently all other carbon atoms of the chain also acquires partial negative charge. Of course, those magnitudes are becoming smaller and smaller. As a result, we neglect these negative charges which are lying after carbon number 2. Now this introduction of partial negative charge by the atoms or certain group of atoms which itself requires partial positive charges is called what? Plus I effect. Plus I effect. Definitely we can easily make out plus I effect will be shown by only those species which are what? Less electronegative than carbon. We also regard, like with respect to this, like we can take N-butyl, this carbon chain actually was giving electron towards oxygen. That is why it was releasing electron, it was giving our electron to the OH group. We call it that this alkyl chain shows plus I effect. So what we find is tertiary groups followed by secondary group, followed by primary group, and followed by this methyl. This is the decreasing order of the plus I effect. Plus I effect of the alkyl chains, because tertiary will be having inductive effect from 3 sides. Definitely this makes the tertiary one to be what having the strongest plus I effect. The actual reason of this plus I effect of this the alkyl chains lies in the hyperconjugation, which we'll be doing later on. Now let us see the resonance structures and resonance effect. See, we know that the delocalization of pi or lone pair electrons all along the carbon chain, which leads to the formation of high and low electron density areas, is called resonance. It's a very strong phenomenon, very important phenomenon, and what we find is that those molecular species in which it exists becomes very, very stable. Let me give you an example of this. Like this molecular species is we call it buta-1,3-diene. In this, what happens is, we believe that this bond length CC double bond must be of 1.34 angstroms unit, then this single bond will be of 1.54 angstroms unit, and this again should be of 1.34. But what we find is, since this electronic movement takes place like this, the pi bond gets shifted to this carbon, and as a result this shifted towards here, and we acquire another structure which is called CH2 plus CH double bond CH CH2 minus. What we find is that central one becomes double, and as a result we represent it by an hypothetical structure which is like this. And what we do is we put like dotted bond here, which show that it's a partial double bond. And what we find is all these 3 bond lengths are equal, and they all are of 1.39 angstroms units, which shows that what is happening is delocalization of the pi electrons is taking place all along the carbon chain, and as a result what we are having is all CC bonds getting converted into a partial double bond. Now this delocalization of pi electron all in the carbon chain is called resonance. We also know a very interesting thing is that these 2 structures are called resonating structures or canonical structures. All these are hypothetical structures which are maybe very close to the actual real molecular species, but we know that these are not the actual these are not representing the actual molecule. We represent this molecule by, this is called also called hybrid structure with the molecular species. But nowadays we've always preferred to represent the molecular species with these resonating structures because we believe that they are more closer to what the resonant actual molecular species. Now, what we need to know is that we know the same. Now, this delocalization gives this molecular species more stability, that means lower energy, and this difference of the actual energy and the experimental energy is called what? Resonance energy. And that is the energy by which the molecular species gets still more stabilized. Like we know, the benzene is having a resonance energy of almost 151 kilojoule per mole. So, this is how it makes a lot of difference. Let us discuss now the resonating structures of benzene. We know that benzene is having what? 3 alternate single double bonds, which can be written in this form also. So these are the 2 resonating structures we have in case of benzene. Now what happens is, when we attach certain molecular species and they get involved in the resonance of the molecular species, and they start, because of which they start getting what? Affecting the physical and the chemical properties, specifically chemical properties of the compound, we call it resonance effect. Now, let me explain it to you. This resonance effect is of 2 types. It's called minus R and it's called plus R. How we distinguish this one? Let us take an example of phenol. Now, what we find in case of phenol is that this oxygen is having a lone pair. Now, we know that movement of electrons always in the molecular species in covalent compounds due to resonance or because of the resonance is always from lone pair towards pi bond system. So, it will shift towards this side and this will shift towards this side. So, what we acquire is this resonating structure in which what we find is oxygen becomes what? Positively charged, and the carbon number 1 becomes what? Carbon number 2 becomes negatively charged. Then this carbon, the negative charge of carbon number 2, which is at ortho position, shifts towards 3 and the 3 pair shifts towards 4. So the next resonating structure which we get is almost as like this, in which what happens is, of course, there's a positive charge on the oxygen. What we find is the negative charge shifts to para position 4th carbon. Now from here it shifts towards what? At the carbon number 6. So the next resonating structure which we can draw is like this. The negative charge appears at carbon number 6. And what we find is that 2 new bonds are formed between 4 and 5. Now this negative charge from carbon number 6 gets shared between carbon number 6 and 1, and this oxygen acquires its pair back. So the next resonating structure which we get is like this, in which what we find is that the positions of the double bond gets changed. Oxygen still again acquires the 2 lone pairs. And now what we find is that the structure number, like if we number them 1, 2, 3 and 4 and 5, what we find is structure number 1 and 5 are exactly same. The only difference is that the position of the double bonds has been changed, and this shows that the complete movement of the lone pair is taking place all along the molecular species, and that is why the position of the double bonds has been changed. Now, this kind of resonance which affects the properties of this phenol molecular species, in which the OH group is actually donating electron towards what? Benzene ring, itself acquiring the positive charge. This positive charge is called plus R effect. Now remember, all those molecular species whose atoms through which they are bonded to the resonating species or the covalent carbon molecular species, if they are having, those atoms are having lone pairs, definitely the movement takes place from those lone pair towards those covalently bonded or pi bond systems, and therefore they acquire positive charge, and all those such species will be showing plus R effect. Now, since they stabilizes the benzene ring by introducing negative charge towards them, we call them ring stabilizing groups. And since they introduces negative charge at ortho and para positions, we call them what? Ortho para directing groups, because electrophilic substitutions now will take place at ortho and para positions. What other groups we have which shows plus R effect is, let me give you a short list of this. The plus R effect will be shown by, definitely, yes, we have seen how the OH shows. Similarly, we can have NH2 group, we can have O ethers, we can have NH secondary amines, we can have NR2 tertiary amines, we can have amides like this. So all these groups will be showing what? The plus R effect. Now let us see how the minus R works. The minus R effect is shown by those groups which actually takes out electron from the benzene or the resonating system. Let us take example of benzaldehyde molecular species. Now in this what happens is, since carbon is bonded to a more electronegative oxygen, this oxygen withdraws electron, pi electron, which is sharing with the carbonyl carbon. As a result, what happens is one pi bond, pi pair of electrons gets shifted towards this carbonyl carbon, and therefore what happens is carbon number 2 acquires partial positive charge, and what we get a structure like this. So carbon number 2 acquires partial positive charge, and it is like this. Now this carbon number 2 asks for the electrons from carbon number 3, which withdraws the pair which it is sharing with carbon number 4, and this is how what we get is that this positive charge which was at ortho position gets shifted to para position. We got a new bond at carbon number 2 and 3, and rest of the structure remains the same. Oxygen is having a negative charge and hydrogen, and this is how the positive charge is now at carbon number 4. Now carbon number 4, being electron deficient, asks for the electrons from carbon number 5, which withdraws its pair of electron which it is sharing with carbon number 6, and this is how the pairing shifting takes place, and what we get is this structure in which the positive charge comes at, and it appears now at carbon number 6. This is 1, 2, 3, 4, 5, and 6, and new bond is formed between 4 and 5, and it is already there between 2 and 3. Now what happens is this carbonyl carbon donates its pair of electrons pi to carbon number 6, so that the bond is formed between carbon 1 and carbon 6, and the oxygen gives back its pair to the carbonyl carbon, so that what we get is we get this structure back, in which we have a perfect this aldehyde group. But what we find is that this fifth resonating structure is very similar to the first one. The only difference is that the pair of the position of the double bonds has been changed, which shows that the complete rotational movement of the pi electrons all along the carbon compound is taking place. But what we find is that this aldehyde group is withdrawing electron from the benzene ring, introducing positive charge at ortho and para positions on the benzene ring, itself acquiring a negative charge, as we call it minus R effect. Now these such groups destabilizes the benzene ring by introducing a positive charge on it, and therefore, and what we find is such molecular species or such compounds will be able to show electrophilic substitutions easily, because they are introducing positive charge on the benzene ring. Another interesting thing is this, that even if we try to introduce what electrophilic substitutions to take place on these molecular species, then electrophilic substitutions will take place definitely under drastic conditions with difficulty, and only at meta position, because that is the only place where there is no positive charge. So let us take now a look of those molecular species which will be showing minus R effect. Remember, minus R will be shown by those groups which are not having any lone pair on the atom through which they are bonded to the carbon system. Rather, they will be bonded to more electronegative atoms, like we see the aldehyde group, acid group, nitro group, acyl group, ester group. We can also have amide group. So all these are the examples where what we find that these are the groups which shows minus R effect. The next electronic displacement effect is electromagic effect, which is also called E effect. See, it's the movement of the pi electron system, or in a multiple bond system, to any one of the bonded atom under the influence of the attacking reagent. It's a temporary effect. Remember, let me explain it to you. Like suppose we were having an alkene. Now in this alkene we know that there is high electron density already, because the pi electrons are moving between the two carbon atoms. So when this species is introduced, any electrophile, what happens is, under the influence of this attacking reagent, pi electrons shift toward one of the carbon atom, which attracts this H plus, and what we find is this is how this acquires this H. And this attack of this electrophile on this non-polar multiple bond system is called plus E effect. We call it plus E because the attacking species is already a positively charged species, and it is leading to the formation of a carbocation, and that is why what we find is that the non-polar multiple bond systems always shows electrophilic plus E effect, electromagic effect, and they always shows electrophilic addition reactions. because they are the only species which will be getting attracted towards these non-polar multiple bond systems. On the other hand, if suppose we were having this carbonyl group, what we find is that if we are introducing the electrophile as well as both nucleophile, in this also we can introduce nucleophile also, but nucleophile will not be attracted because the high electron density of this alkene will repel this nucleophile, and therefore that is why what we find is that alkenes, alkynes, benzene and others never shows nucleophilic addition reactions. Now let us take this example of a carbonyl carbon which is representing the polar multiple bond system. In this what happens is that of course we think that initially that this oxygen's electron density will be attracting this electrophile, but no, this doesn't happen. What happens is this, we know that this bond is already polar, and what happens is under the influence of this attacking reagent nucleophile, this nucleophile attacks this electron deficient carbonyl carbon, due to which the shifting of the pi electron takes place on the oxygen. And as a result what we find is the cyanide becomes part of this carbon and the oxygen acquires partial negative charge. Now this shifting of this pi electrons to more electronegative atom in a polar multiple bond system by this under the influence of this coming or attacking nucleophile is called minus E effect. We call it minus E because the attacking species is a nucleophile. So this is how what we find is all polar multiple bond system shows what nucleophilic addition reactions, and all non-polar multiple bond system shows plus E or electrophilic addition reactions. The next electron displacement effect is called hyperconjugation. See, it's the shifting of the sigma electrons of the CH bond of the methyl group to the next neighboring electron deficient or multiple bond system. Let me give you an example. Like suppose we are having what, this propene molecule. Now in this propene molecule what happens is, at some part of a time definitely the pi electrons which are moving between the two carbon atoms can shift to this carbon, and as a result this carbon becomes electron deficient. It will ask for the electrons from this carbon, which due to which what happens is this withdraws electron from one of the hydrogen and starts sharing it with this. Now what happens as a result is what we find is this becomes what, this hydrogen becomes positively charged, we get this, and this is how we acquire this structure. Now in this structure what we find is this hydrogen becomes electron deficient, becomes positively charged species. It is not allowed to move out because it is still hanging in the p-orbitals of this sp2 hybridized carbon, because at the very next moment what happens is this backward movement takes place. But what we find is which we think is a sort of a resonance, is what is involving this sigma bond. Shifting of the sigma bond is taking place, and as a result what we are finding is to this pi bond system or to the very next carbon, which is actually either a part of a double bond system or a multiple bond system or is electron deficient. So this kind of shifting is called hyperconjugation. It's a permanent effect, and as a result what we find is the delocalization of the sigma electron is taking place, which is giving what, the stability to this molecular species. Now in this particular propene what we find, or in the alkene what we find is this methyl can give hydrogens from the three different hydrogens. The pair, this carbon can donate this pair from three different hydrogens. So this particular species will be having three hyperconjugating structures. So it's like very similar to resonance. We call it a no bond resonance or extension of resonance. The reason being because we cannot say it to be a resonance because here the sigma bond is involved. But yes, like resonance, more of the hyperconjugating structures we have in a molecular species are a little bit stability. That is what the reason is which makes what this methyl carbocation, primary carbocation, very stable than the methylene carbocation. Because what happens is, let me tell you, like if suppose this carbon is electron deficient and its very next methyl can withdraw electron from hydrogen and can share it with this. So the structure becomes what, CH2 plus H plus. So this H plus requires positive charge. This becomes double bond and this is CH2. Now in the very next moment this electron comes back and what we get is the structure back. So that is how it means this primary carbocation will be having what, how many hyperconjugating structures? 3 hyperconjugating structures. And that is the reason is because of this secondary becomes much more stable than what this primary carbocation. Why? Because this will be having 3 hyperconjugating structures from this methyl and 3 from this. That is what the total becomes 6 hyperconjugating structures. And that is again there is a reason which makes what this tertiary carbocation the most stable. The reason being this will be having 9 hyperconjugating structures. So hyperconjugating structure Hyperconjugation not only is the reason which is behind the stability of this carbocations or even the free radicals, it is also behind the stability of the alkenes, and that is what we say that the most substituted alkene is most stable. Now let me give an example, like if we take this one, this alkene. This is most substituted. All the 4 hydrogens of this alkene has been substituted by methylene groups. This will be having what, 3, 3, 3, 3. So total of 12 hyperconjugating structures, which makes this 2,3-dimethyl-butene very, very stable alkene. So this is what we have hyperconjugation. Now let us see the types of organic reactions which we normally find taking place in the organic compounds. The organic reactions of organic compounds can be divided mainly into 4 major categories. The first category is of substitution reactions. Substitution reactions, these are the reactions in which one species substitutes the other one, and this is being shown by almost all types of hydrocarbons, alkanes, alkenes, alkynes, and derivatives. Then the second category is of additional reactions. This is only shown by those compounds which are unsaturated. Definitely by alkenes and alkynes are not shown by alkanes because they are already saturated. And what we need to understand at this stage is that in this what happens is the smaller molecules or molecular species are added on the multiple bond system so that the pi bonds are no more there in the compound, and due to those pi bonds what happens is the addition of the molecules takes place on the organic compounds. So such reactions are called additional reactions. The third category is of elimination reactions. The elimination reactions are exactly just the opposite of the additional reactions. In elimination, smaller molecules are actually being taken out of the molecular species, bigger molecules, and as a result what we find is unsaturation is created. Pi bonds are formed. So in addition, the pi bonds actually are broken down, and addition takes place on the place of the pi bonds, and in this the groups are withdrawn or taken out, and on their place the pi bonds are formed. So these are called elimination reactions. And then we have the last category, which belongs to the rearrangement reactions. The rearrangement reactions, in fact, are the reactions which basically are the largest in the number if we consider all the organic reactions taking place around us. So, what are rearrangement reactions? In these, what happens is the reactant molecules rearranges themselves, or the intermediate forms during the reaction rearranges themselves in order to form a much more stable product. So that is how we get rearrangement reactions.